In our last lecture, we went over the phases of matter, we went over all the gas laws, and we went over the triple point and the heating curve. Okay, some common questions we see on the SAT too. Now in this lecture, I'd like to go over what atoms are, atomic theory, okay, and all the scientists that had contributed something to discovering the atom as the smallest unit of matter. Okay, so first thing is all matter is composed of atoms. Otherwise, you're not matter, okay, and that's pretty simple. Secondly, all atoms of a given element are alike. Now, we're going to refute this, okay? Just keep in mind, this is atomic theory. Isotopes would be the exception to that. Isotopes have different masses, and so they're not all alike, okay, but that's okay, we'll do that later. Compounds are made up of atoms combining atoms in fixed proportions, right, as we said before. H2O is a perfect example. For every 2 atoms of hydrogen, we have 1 atom of oxygen. And finally, a chemical reaction involves the rearrangement of atoms. This is a chemical change that we did in lecture 1. We know that, okay? We know that there's reactants and it yields, or with an arrow, to products. All right, so the first scientist is Robert Amilikan, and he did this oil drop experiment. Basically, he read Einstein's paper on the photoelectric effect and about light being a particle. And he was like, no, light's a wave. Anyway, by using this atomizer, he actually discovered what was the mass and the charge of an electron. And really, an electron is really, really small. It's like 1 over 1,834. It's like really, really small. So for the most part, the mass of the electron, we're going to count that as 0. We're going to say that electrons have no mass because it's so small, it's negligible. Okay, and the charge, he found out that it was negative. Okay, by having these 2 electric plates, he's got his little electrodes over there, and it's the oil drop. He sprays the oil, psst, okay, he sees which way it goes. All right, the next one is Ernest Rutherford. You can't get through without Ernest Rutherford. Ernest Rutherford has these alpha particles, which are positively charged. Okay, and so they're really tiny. Really what they are the nucleus of a helium atom. And so you can also write an alpha particle like this, with helium like this. Put 4 on the top and 2 on the bottom. It's a helium nucleus. He shoots them at this gold foil that's so thin, like 13 atoms thick. Okay, it's really, really thin. And he shoots them. Okay, and as he's shooting them, most of them just go straight through. But then all of a sudden, some of them like angle off to other sides. In fact, a couple of them came right back to the alpha gun. When he saw that, okay, he wrote in his journal that it was similar to taking a Cougar Magnum, okay, aiming it at a piece of toilet paper, and the bullet coming back, okay? The bullet bouncing off the toilet paper. Why did the alpha particle bounce off 13 atoms of gold? Very thin sheet. It should go right through. How can this be possible? Okay, and so this is where he comes up with what the atom is all about. Okay, now remember, gold is really big atoms. Alpha particles are really tiny, and yet they still smashed into each other, like something really big. Sometimes it would shoot this way, sometimes go up this way, but once it hit the middle, okay, and you know that the nucleus is positively charged, alpha particles are positively charged. And so Ernest Rutherford's findings are that the atom is really a bunch of empty space, okay? That if I were to take like, let's say we're standing in the middle of Yankee Stadium, and I took the nucleus of a gold atom, and I increased it to the size of a golf ball, the first electron would be found all the way in the last row. All that space, okay, from the nucleus to the last row, atoms are mostly empty space. And the nucleus is actually quite small compared to the entire size of the atom. The atom is like so big, but then the nucleus is like this big. Okay, and that's really where all the mass is. The outside is all empty space and electrons moving through it. So these are great findings. All right, another thing is that the nucleus has a positive charge and that most of the mass is condensed to the middle. So this is really big. Okay, next. So after all this, we have some scientists that Goldstein discovers protons, Chadwick with neutrons, Thomson with the electrons. Okay, it's nice to just know those for the true and false questions that come up. They usually don't ask scientists on the multiple choice questions. Okay, then the mass is 1 AMU. This stands for atomic mass unit. Okay, so 1 atomic mass unit is a proton, 1 atomic mass unit is a neutron. And then electrons, now their location, these are the nucleus, the location here would be in orbitals. Let's take a look at other theories now. So isotopes, okay, so they have the same atomic number but different number of neutrons. As I mentioned before, we were going to fix this, okay? So for example, we have 3 versions of carbon, 12, there's carbon 13, and carbon 14. All 3 of these are carbon, except that We know they're carbon because they have exactly 6 protons in their nucleus. The bottom number is the atomic number. The top is going to be the atomic mass, right? This is my mass. And they each have a different mass. And so what we do is we take the average of all the atoms that exist, right? And then we come up with some atomic number. If you look at the atomic number for carbon, it's like 12.001. It's like this weird decimal. The actual one, that's because we've taken, what? We've taken 98%. This is 98%. This is about 0.5%. And this is about 1.5% of these isotopes, okay? And then all you have to do is multiply that by 12, multiply that by 13, multiply that by 14, okay? And then you'll add them all up, and then you'll get 12.0001, or whatever it is. Okay, so isotopes very important. The other thing is they have different number of neutrons, okay? So that's why they're heavier. They don't have a different number of protons. As you saw in those carbons, they all had 6 protons, but then carbon-12 had 6 neutrons, carbon-13 had 7 neutrons, carbon-14 had 8 neutrons, which made it unstable, right, and radioactive, which we'll get to in another chapter. Okay, so now the Bohr model of the atom, this is your plum pudding man. Okay, he believed that the electrons circled around in orbitals, okay? He was the one who said this. He also mentioned that they can jump orbitals. In other words, they can go from one state, a ground state, to an excited state, right? So this was the ground state. We could just put ground here. Okay, what happens is electrons absorb energy, and the electrons up here, and they get excited. This will be the excited state. Right, and then when they come back down to the ground state, they emit light. Okay, light is emitted. And so this is huge, right? Excited state at a higher energy level. All right, great. So let's look at this a little closer and the other theories that come with this, okay? Because the Bohr model of the atom gives us this line spectra that we should know, because that light that's emitted, okay, could come in different wavelengths, and we can measure that, because for every single element, it's unique. They have a different line spectrum, okay? So this comes from the Bohr model. We can measure how much energy an element absorbs based on the colors that it emits. And this one, for example, is the hydrogen line spectrum. Okay, they call this the Balmer series. Be aware of this. Okay, next thing, the wave mechanical model. All right, so PEL stands for principal energy level. And so we're taking what Bohr said of the atom and just going a step further, talking about the energy levels. And so the energy level would have, number one, would have only 1 subshell. Energy level 2 will have 2 subshells. Energy level 3 has 3 subshells, and energy level 4 has 4 subshells, okay? Speaking of which, what are they? Well, subshell for the first one would just be S. This would be S and P. This would be S, P, and D. And this would be S, P, D, and F. Okay, very nice. So these are the ones they represent, and we'll look at these a little closer, but I could put it over here. So S holds 2 electrons, P holds 6 electrons, okay, D holds 10 electrons, while F can hold 14 electrons. And so this is going to lead us into now electron configuration. Okay, but before we get there, let's get this out of here. Let's erase this. Okay, and talk about first 2 very important rules. I love going over these scientists because they show up on the true and false, so we want to be aware of it, and like as if we read the textbook. And so the Pauli exclusion principle is basically saying, hey, electrons, opposite spins. Why do electrons have to have opposite spins? The reason why is because electrons are both negative. And we know that same charge repels, opposite charge attracts. And so if we have 2 negatively charged electrons over here, they want to be as far away as possible. So they'll have opposite spins. And so for example, hydrogen has 1 electron, so we point with the 1 arrow. But helium has 2 electrons. Those 2 electrons should be spinning in opposite directions. Okay, and then we're asking you in this question, which of these breaks Pauli's exclusion principle? Which one of these pictures does not obey this rule that they're supposed to have opposite spins? Okay, as we can look, as long as you're in a different orbital, you're fine. But if you occupy the same, you're doing the wrong thing. And so that's what's happening right here with A. Okay, where are the opposite spins? Not cool. All right, what else? Oh, right here. Why don't you have opposite spins? Okay, and so these 2 break Pauli's exclusion principle. They should never be pointing in the same direction. Okay. Number 2 is Hund's rule. Hund's rule states that you cannot occupy, electrons cannot occupy an orbital until it's completely full. All right, so for example, they're not going to pair up. right? So for boron, it's 2p1, 1 electron. 2p2, for carbon, 2 electrons. Hey, how come they didn't pair up? They didn't pair up because electrons are negatively charged and they want to be away from each other. And remember, the p orbital can hold 6 electrons. Each one of these, okay, are different orbitals, right? So are subshells. So p3, we have electron occupying all 3. Okay, now once we get to 4, they start to pair up. We start to see electron pairs. But there's no electron pairing over here. There's no electron pairing here or here. Okay, similarly, I had put oxygen over here. Watch what happens. That would be the next one, right? And we had said over here. But what I'm showing you here is the 1s orbital, 2 electrons, full. 2s orbital, 2 electrons, full. Giving us the total, right, of 7 electrons. That's what nitrogen's supposed to have. Oxygen has 8 electrons. 2 in the 1s, 2 in the 2s, and then we have our 4 in the p orbital. Okay, that should actually say 2p. All right, now looking at this, how do we get electron configurations? I want you to remember like this. The first 2 columns, all right, that would be the alkali metals, and the alkali earth metals are going to be s orbital. Okay, coming over here, we have our p orbital can hold 6 electrons, and so anything so right over here, this would be group 13. Group 13 all the way to group 18, the noble gases, this would all be the p orbital. Okay, and then we have the d orbital. This would be all our transition metals that are found in the middle. And then the f orbital would be over here. I also like the fact that it shows us 1s, okay, and then this should also be 1s. So this would be 1s1, 1s2, 2s1, 2s2, 2s3, no, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, and so forth. So let's take a look at it this way, right? You start with 1s, then you go to 2s, 2p3s, 3p4s, and then you should memorize this. Okay, so knowing the exact order plays a big role. 3d, 4p, 5s, and so forth. Okay, so let's take a look at an actual problem. What's the electron configuration for sulfur and calcium? Step 1, how many electrons does each one have? So sulfur has 16 electrons and calcium has 20 electrons. Then what I'm going to do is I'm just going to put S here. Okay, so there's sulfur. I need 16 electrons. So the first shell we always fill is 1s. Okay, so 1s2. Now we go to 2s2. All right, I'm just going to go backwards for a second and show you what I just did, right? 1s, 2s, next is 2p, and then 3s. Okay, so then I go to 2p6. Right? Now, these exponents here represent the number of electrons. So already I have 10 electrons. But I need 16, so we keep going. The next one after 2p is 3s2. Okay, and then I need 3p what? Okay, so that's 12. And so I need 4 more, and that is going to be the electron configuration for sulfur. Okay, great. Now, you could do this another way. This whole thing here stands for neon. Neon has that electron configuration. And so if you want to do the shortcut, you could just write neon 3s2, 3p4. That looks nice. Now, what about calcium? Calcium's electron configuration. Okay, start off, we have 1s2, 2s2, 2p6, 3s2, 3p6. Right there. Okay, I already have 18 electrons, okay? Now I need 20, so I go to the last one, 4s2. And going back over here, after 3p comes 4s, no problem. And you can just see that right on the periodic table, how nicely that looks. Okay, with this still in the way, I just wanted to show you that calcium would be the 4s. Calcium is found right there, element number 20. Okay, well, I have 3p4 for sulfur. Okay, sulfur is right there. I can pick it right on the periodic table. Very nice. And could I write this in a shorthand way? Sure, I could. All of this, okay, is argon. Argon has 18 electrons. It's the 18th element. And I could just write it as 4s2. And that's usually how you would see it. You'd see it in the shorthand way on the SAT too. Okay, so now last thing we should go over today is the Lewis dot structure. So what are valence electrons? These are basically the electrons on the furthest end. Okay, so basically these are your most outer shell electrons. So for example, all the elements on the first group have 1 valence electron. All the elements over here have 2 valence electrons. Skip the transition metals. Okay, moving on. Here we have 3 valence electrons, 4 valence, 5, 6, 7, 8. You could just count straight across. So this makes it like pretty simple. Valence electrons are electrons that are in the outermost principal energy level. Okay, that's a better definition than what I said. Okay, so now can we draw the Lewis dot structure? So basically you have to draw a dot for all the valence electrons. And so let's take a look at sodium. It's going sodium, this is how we're gonna look at it. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Let's look at these elements. So sodium has 1 valence electron, and so you'd put it right there. While magnesium has 2 valence electrons. And aluminum has 3. Okay, now notice I filled in the first 2 up on the top. I did that on purpose because that's the s orbital, and that needs to be filled. Silicon, see now I'm spreading them out more because they were paired according to what Pauli exclusion principle, Hund's rule. So then we have phosphorus, we spread them out like that. Sulfur, and then we can start pairing them, okay? And then chlorine has 7 valence electrons. And then finally argon, you can fill the whole thing up. All the noble gases have fulfilled this thing called the octet rule. The octet means that they want 8 valence electrons to be satisfied in their outer shell. And so this is nice. Okay, we'll look at exceptions to the octet rule and bonding next time. But guys, this is the end of this lecture. All right, keep on studying and remember, be safe.